Welcome to DAR Tutors. Today, we're going to explore a fundamental concept in chemistry, the rate of chemical change. This topic is a cornerstone of the IB Chemistry Higher Level curriculum. And by the end of this video, you will be able to explain the factors that influence reaction rates, analyze kinetic data, and understand the mechanisms behind chemical reactions. The central question we will address is, how can the rate of a reaction be controlled? Understanding this is key to optimizing industrial processes, controlling biochemical reactions in our bodies, and predicting the lifetime of various materials. Our first objective is to define the rate of reaction and introduce the fundamental model for how reactions occur. First, what is reaction rate? Simply put, it's a measure of how quickly concentrations of reactants or products change over time. It tells us how fast a chemical process is proceeding. We can express this mathematically. The rate can be defined as the change in the concentration of a particular reactant or product divided by the change in time. Notice the negative sign for reactants. Their concentration decreases, so we need the negative to keep the rate positive. For products, their concentration increases, so the rate is positive. Next, let's explore collision theory, the simplest model to explain how reactions happen. Collision theory states that for a reaction to occur, particles must collide with each other. However, not every collision results in a reaction. According to collision theory, a collision must satisfy two criteria to be successful. First, the particles must collide with a kinetic energy greater than or equal to a minimum value called the activation energy. And second, they must collide with the correct orientation or collision geometry. We call these successful or effective collisions. Consider two nitrogen dioxide molecules, NO2. If they collide with their oxygen atoms facing each other, they will likely just bounce off. This is an unsuccessful collision due to incorrect orientation. But if they collide with their nitrogen atoms aligned, they have the potential to form dinitrogen tetroxide, N2O4. This is a successful collision. Another example is the bromination of ethene, which involves a steric effect. The bromine molecule must approach the pi bond of ethene sideways on for the electrophilic addition to occur. This specific geometric requirement is another manifestation of correct orientation being crucial. In summary, we've defined reaction rate and explained collision theory, understanding that successful reactions require both sufficient energy and correct orientation. Let's now focus on the energy aspect of collision theory and explore the concept of activation energy. Our objective here is to define activation energy and interpret reaction energy profiles. Activation energy, symbolized as E sub A, is the minimum amount of combined kinetic energy that a colliding pair of particles must possess for a reaction to occur. Think of it as an energy barrier that particles must overcome. Even if particles collide with the correct orientation, if their kinetic energy is less than the activation energy, they will simply rebound without reacting. This is why faster reactions are associated with lower energy barriers. This energy barrier can be visualized using a reaction energy profile, like the one shown. The y-axis represents potential energy, and the x-axis represents the progress of the reaction. Reactants start at one potential energy level, and products end at another. Between them is a peak. The height of this peak above the reactant's energy level is the activation energy, E sub A. The species that exists at this peak is called the transition state. The transition state is a short-lived, high-energy, unstable species where old bonds are breaking and new bonds are forming. It cannot be isolated. Intermediates, which we'll discuss later, have fully formed bonds and exist at potential energy minima, making them more stable and sometimes isolatable. So, to recap, activation energy is the minimum energy required to reach the transition state and initiate a reaction. It is represented by an energy barrier on a reaction energy profile. Now, let's connect our knowledge of collision theory to the observable factors that affect reaction rates. These are the levers we can pull to control a reaction's speed. Our objective is to explain how key factors influence reaction rate based on collision theory. We will examine concentration, pressure, surface area, and temperature. First, concentration. Increasing the concentration of reactants in a solution means there are more particles per unit volume. This leads to an increase in the frequency of collisions between reactant particles. More collisions per unit time means a greater chance of successful collisions, and thus, a faster rate of reaction. For example, magnesium reacts faster in concentrated hydrochloric acid than in dilute hydrochloric acid, because the higher concentration of hydrogen ions results in more frequent collisions with the magnesium surface. Next, pressure, which applies to gaseous reactions. Increasing the pressure on a gas forces the particles into a smaller volume. This effectively increases the concentration of the gas particles. Just like with solutions, this higher particle density increases the collision frequency and, consequently, the reaction rate. A key point to remember is that changes in pressure have a negligible effect on the rates of reactions in solutions or solids, as liquids and solids are incompressible. Third, surface area. For reactions involving solids, the reaction can only occur at the surface where particles are exposed. Increasing the surface area of a solid reactant by breaking it into smaller pieces increases the number of available sites for collisions. This leads to more frequent successful collisions per unit time and a faster reaction rate. As this diagram shows, a large cube has a surface area of 54 square centimeters. If you cut it into 27 small cubes, the total volume remains the same, but the total surface area dramatically increases to 162 square centimeters, making the reaction much faster. In essence, these factors, concentration, pressure, and surface area, all work by increasing the frequency of collisions, thereby speeding up the reaction. We have now explained how these factors influence reaction rate. Now let's examine the final and often most powerful factor, temperature. Its effect is more complex and requires a new analytical tool. Our objective is to use Maxwell-Boltzmann curves to explain how temperature and activation energy affect reaction rate. We use a Maxwell-Boltzmann energy distribution curve. This graph shows the distribution of kinetic energies among molecules in a sample. The y-axis is the number of particles, and the x-axis is their kinetic energy. A top tip is that temperature is a measure of the average kinetic energy of the particles. So at any given temperature, particles have a wide range of energies, not a single one. Recall that a reaction requires particles to have at least the activation energy, E sub A. On this curve, we can mark E sub A. The area under the curve to the right of E sub A represents the number of particles with kinetic energy equal to or greater than the activation energy. These are the particles that are capable of reacting upon collision. So we can see why a higher activation energy leads to a slower reaction rate. Fewer particles possess the required energy. Now what happens when we increase the temperature, say from T to T plus 100? The Maxwell-Boltzmann curve changes shape. First, the curve flattens. This is because the total number of particles and the total area under the curve must remain constant. Second, the peak of the curve shifts to the right. This indicates that the most probable kinetic energy and the average kinetic energy of the particles have increased, which aligns with our top tip that temperature is a measure of average kinetic energy. But most importantly, look at the area to the right of E sub A. For the higher temperature, this area is significantly larger. This means a much greater proportion of the particles now possess enough kinetic energy to react. So, increasing the temperature has two main effects that increase the rate. First, particles have greater velocity, leading to more frequent collisions. Second, a much larger fraction of those collisions are successful because more particles have energies greater than or equal to E sub A. This second effect is usually the dominant one, which explains why a small temperature increase can have a large effect on reaction rate. For many reactions near room temperature, a 10 °C rise can double the initial rate. We've discussed how the reaction energy profile shows the energy barrier, E sub A. Now let's explore a very powerful tool to control this barrier, catalysts. Our objective is to define catalysts and explain how they work, visualizing their effect on the energy profile and the Maxwell-Boltzmann distribution. A catalyst is a substance that increases the rate of a chemical reaction without itself being chemically changed in the process. It doesn't get consumed, it just facilitates the reaction. So how do they do this? A catalyst works by providing an alternative reaction pathway, or mechanism, which has a lower activation energy barrier. This is often visualized with the mountain pass analogy. If reactants have to climb over a tall mountain peak to become products, that's like an uncatalyzed reaction with a high E sub A. A catalyst is like a tunnel or a mountain pass through the mountain. It offers a much easier, lower energy route. We can see this clearly on an energy profile. Here is the uncatalyzed pathway with its high activation energy. Now let's add the catalyzed pathway. Notice that the reactants and products are at the same energy levels, so the overall enthalpy change, delta H, is unchanged. What has changed is the activation energy. The catalyzed path has a significantly lower E sub A. In fact, for multi-step catalyzed reactions, the mechanism often involves several smaller, lower energy peaks instead of one large one. Now let's see this effect on the Maxwell-Boltzmann curve. Here's our original curve and the activation energy, E sub A, for the uncatalyzed reaction. Only the particles in the orange area can react. When a catalyst is added, the activation energy decreases to a new lower value, E sub A prime. Now, the area to the right of E sub A prime is much, much larger. This means that at the same temperature, a significantly greater proportion of the sample particles now have sufficient kinetic energy to overcome the energy barrier and react. This dramatically increases the reaction rate. So, a catalyst doesn't give particles more energy. It simply lowers the energy requirement for a successful collision by providing a new, lower energy pathway. Catalysts can be classified in different ways, and understanding these classifications is important. Our objective is to distinguish between homogeneous and heterogeneous catalysts. We classify catalysts based on the phase or physical state of the catalyst relative to the reactants. A catalyst is called homogeneous if it is in the same phase as the reactants. For example, if both the reactants and the catalyst are dissolved in water, it is a homogeneous system. An excellent industrial example is the use of vanadium V oxide in the contact process for sulfuric acid production, which is a homogeneous catalyst. Sulfuric acid is the most produced industrial chemical worldwide, so this process is of immense importance. In contrast, a catalyst is called heterogeneous if it is in a different phase from the reactants. Heterogeneous catalysts typically provide a solid surface for gas or liquid phase reactions to occur on. A practical example is the decomposition of hydrogen peroxide, H2O2, into water and oxygen. The aqueous hydrogen peroxide is a liquid, but the catalyst, solid manganese IV oxide, is a solid. This is a heterogeneous catalyst. The reaction takes place at the surface of the manganese bi-4 oxide. After the reaction, because the catalyst is in a different phase, it's easy to separate. You can simply filter it off and reuse it. This ease of separation is a significant advantage of heterogeneous catalysts. In summary, a catalyst can be homogeneous if it shares the phase of the reactants, or heterogeneous if it's in a different phase, often providing a surface for the reaction. Let's apply these concepts by looking at the detailed mechanism of a famous industrial reaction, the Haber process. Our objective is to use the Haber process as a case study to understand the mechanism of a heterogeneous catalyst. The Haber process is the synthesis of ammonia, NH3, from nitrogen, N2, and hydrogen, H2. This is an exothermic reaction. It is heterogeneously catalyzed by a solid iron catalyst, which is often promoted by other substances like aluminum oxide. The reaction mechanism is thought to occur in 4 main steps at the catalyst's surface. First, we have adsorption. Nitrogen and hydrogen gas molecules land on the iron surface and stick to it. This is like they're being held in place. Next comes dissociation. Because they are adsorbed onto the surface, the strong triple bond in N2 and the single bond in H2 can break, turning the molecules into individual nitrogen and hydrogen atoms. Now, the actual reaction occurs. Hydrogen atoms, which are very reactive, combine with nitrogen atoms step by step, forming intermediate species like NH and NH2, until they form the final product, ammonia NH3. Finally, desorption. The newly formed ammonia molecules are no longer bound to the iron surface and leave as a gas, regenerating the active site on the catalyst so it can be used again. This demonstrates the key feature of a catalyst. It is regenerated unchanged. It's important to note that this reaction only takes place at specific active sites on the catalyst surface. If all active sites are occupied, increasing the pressure further will not increase the reaction rate, as there is nowhere else for the molecules to adsorb. So far, we've discussed catalysts in a general sense. Now let's talk about a specific and incredibly powerful class of catalysts: enzymes. Our objective is to describe the features and mechanism of enzyme catalysis using the lock and key model. Enzymes are biological catalysts. They are protein molecules that catalyze biochemical reactions in living organisms. They make reactions happen at incredibly fast rates under very mild conditions, typically body temperature and neutral pH. What makes enzymes so special? They have several defining features. First, they are incredibly efficient, increasing reaction rates by factors of 10 to the power of 6 up to 10 to the power of 12. Second, they are highly specific, usually catalyzing only one particular reaction. Third, they work under mild conditions. Fourth, their activity can be regulated by the cell. And fifth, their activity can be inhibited by other molecules, providing a control mechanism. Their specificity is best explained by the lock and key model. Imagine an enzyme molecule as a lock with a unique three-dimensional active site. A specific reactant molecule called the substrate acts as the key. The substrate's shape and chemical properties are complementary to the active site, allowing it to bind perfectly. This binding forms a temporary structure called the enzyme-substrate complex. Inside this complex, the enzyme facilitates the chemical change. Once the products are formed, they are no longer a perfect fit for the active site, so they are released, leaving the enzyme ready to bind to another substrate molecule. It's a top tip to remember that the active site is actually a complex three-dimensional space, more intricate than simple diagrams might suggest. A critical point about all catalysts, inorganic, organic, homogeneous, or heterogeneous, is how they affect a reaction's equilibrium. Our objective is to explain why catalysts do not affect the position of a reaction's equilibrium. A very important principle to remember is that a catalyst speeds up both the forward and the reverse reaction by exactly the same factor. This means it helps the reaction reach equilibrium faster, but it doesn't change the final position of that equilibrium. To understand why, let's look at the energy profile again. Here's our exothermic reaction. The uncatalyzed forward reaction has an activation energy, E sub A forward. The reverse reaction, from products to reactants, has its own activation energy, E sub A reverse, which is higher in this case. Adding a catalyst lowers the activation energy for the forward reaction to a new value, E sub A prime, forward. Crucially, by lowering the peak, the catalyst also lowers the activation energy for the reverse reaction to the same new peak. This means the energy barrier for the forward reaction decreases by the same amount as the energy barrier for the reverse reaction. Since both rates are increased equally, the equilibrium constant, Kc, and the final concentrations of reactants and products remain unchanged. A catalyst just gets you there faster. This is also why catalysts do not alter the enthalpy change, delta H, or the Gibbs energy change, delta G, for a reaction. These thermodynamic quantities only depend on the initial and final states, which are unaffected by the catalyst. A catalyst only changes the path between them. In essence, a catalyst is like a skilled mountaineer who helps a team reach a summit much quicker. The path is easier, but the starting camp and the summit remain the same locations. Let's pause here for a moment. We've covered a lot about the fundamentals of reaction rates. If you're finding this content helpful, we invite you to contact DAR Tutors. We provide expert tuition in IB, A-Level, and IGCSE curricula in a variety of subjects. Our experienced tutors can offer personalized guidance to help you master challenging topics like this. You can find our contact information on our website. Now let's continue our exploration of chemical kinetics. Up to this point, our discussion of reaction rate has been qualitative. Let's make it quantitative by introducing rate equations. Our objective is to define rate equations, reaction order, and the rate constant. For a generic reaction where A and B form products, the rate can be expressed by a rate equation, also called a rate law. Let's break this down. First, rate is the reaction rate, which we define as change in concentration per unit time. So its units are typically m per second. Second, K is the rate constant. It's a constant for a given reaction at a specific temperature. Its value is temperature dependent and has units that vary with the overall order of the reaction. We'll return to its units shortly. Third, the square brackets denote concentration in moles per decimeter cubed, and X and Y are the exponents to which the concentrations are raised. These are called the reaction orders with respect to reactants A and B, respectively. The most important takeaway here, and a common mistake, is that the orders of reaction X and Y must be determined experimentally. You cannot simply look at the stoichiometric coefficients, A and B, and assume they are the orders. The order of reaction is an empirical value. Finally, the sum of the individual orders, X plus Y, is called the overall order of the reaction. This value is crucial because it directly affects the units of the rate constant. So, we have now defined rate equations, reaction order, and the rate constant, laying the groundwork for analyzing experimental kinetic data. Let's put that theory into practice. Our next objective is to learn how to deduce the rate equation for a reaction from experimental data. Our objective is to deduce rate equations for zero, first, and second-order reactions using experimental data. We will use the method of initial rates. In this method, we conduct a series of experiments where we systematically change the initial concentration of one reactant while keeping others constant, and we measure the initial rate. Consider the reaction between reactants X and Y. We want to find the rate equation, which is in the form rate equals K times the concentration of X to the power X times the concentration of Y to the power Y. Let's say we have the following experimental data. In experiment 1, we start with 0.1 m of X and 0.1 m of Y, and the initial rate is 1.0 m per second. In experiment 2, we double the concentration of X to 0.2 m while keeping Y constant, and the rate doubles to 2.0 m per second. In experiment 3, we double the concentration of Y to 0.2 m while keeping X constant, and the rate quadruples to 4.0 m per second. Let's deduce the orders one by one. First, for reactant X. We compare experiments 1 and 2, where the concentration of Y is kept constant. The concentration of X doubles from 0.1 to 0.2. The rate also doubles from 1.0 to 2.0. This direct proportionality, doubling the concentration doubles the rate, means the reaction is first order with respect to X. So our exponent X is 1. Now for reactant Y. We compare experiments 1 and 3, where the concentration of X is kept constant. The concentration of Y doubles. The rate, however, quadruples from 1.0 to 4.0. Since doubling the concentration increases the rate by a factor of 2 squared or 4, the reaction is second order with respect to Y. So our exponent Y is 2. Combining these, the full rate equation is rate equals K times the concentration of X times the concentration of Y squared. The overall order of the reaction is 1 plus 2, which equals 3. We have now deduced the full rate equation from the experimental data. Now that we know how to find the reaction orders, let's look at a worked example to tie everything together and determine the units of the rate constant. We will determine the rate equation, calculate the rate constant K, and specify its units from experimental data. Consider the reaction between nitrogen monoxide and ozone. No gas plus O3 gas yields NO2 gas plus O2 gas. Here is our experimental data. Our general rate equation is rate equals K times the concentration of NO to the power X times the concentration of O3 to the power Y. First, the order with respect to O3. We compare experiment 1 and 2. The concentration of NO is constant. The concentration of O3 triples from 3.0 sop 10^4 to 9.0 10^4. The rate also triples from 6.6 or 10^5 to 2.0 so 10^4. A triple concentration gives a triple rate, so the reaction is first order with respect to O3. Y equals 1. Next, the order with respect to NO. We compare experiment 1 and 3. The concentration of O3 is constant. The concentration of NO triples. The rate also triples. Therefore, the reaction is first order with respect to NOx equals 1. The rate equation is rate equals K times the concentration of NO times the concentration of O3. The overall order is 1 plus 1, which equals 2. Now let's calculate the rate constant, K. We can use the rate equation and the data from any experiment. Let's use experiment 1. Rearranging the rate equation for K, we get K equals rate divided by the concentration of NO times the concentration of O3. Plugging in the values from experiment 1, we get K equals 6.6 times 10 to the negative 5, divided by 1.0 times 10 to the negative 4, times 3.0 times 10 to the negative 4. This calculates to 220. Finally, let's determine the units of K. We can do this from the equation. The units for rate are m per second. The units for the concentrations in the denominator are m squared. M divided by m squared is 1 over m, or m to the negative 1. So the units for K are moles per liter to the negative 1 second to the negative 1. Alternatively, since the overall order is 2, the units for K can be generalized as m to the power of 1 minus the overall order times s to the negative 1. Here, 1 minus 2 is negative 1, so the units are m to the negative 1 so s to the negative 1. We've been talking about reaction orders, x and y. Now let's see how they connect to the concept of a reaction mechanism, a series of elementary steps. Our objective is to relate reaction orders from a rate equation to the elementary steps in a mechanism. Most chemical reactions are not a single-step collision. They occur in a sequence of simpler steps called elementary steps. The entire sequence is called the reaction mechanism. For example, the decomposition of ozone likely involves 2 elementary steps. The overall rate of the reaction is determined by the slowest step in the mechanism. We call this the rate-determining step, or RDS. Think of an assembly line. The speed of the whole line is limited by its slowest worker or machine. That slow step is the rate-determining step. Crucially, the experimentally determined rate equation is derived directly from the rate-determining step. Specifically, the reaction orders, x and y, correspond to the stoichiometric coefficients of the reactants in the rate-determining step. This means the rate equation gives us a window into the actual molecular events of the slowest step. Another term you need to know is molecularity. The molecularity of an elementary step is the number of reacting particles taking part in that step. If one molecule reacts, it's unimolecular. If 2 molecules react, it's bimolecular. If 3 molecules react, it's termolecular. Termolecular steps are rare because they require a 3-body collision, which is statistically improbable. Let's work through an example of evaluating a proposed reaction mechanism. Our objective is to evaluate a proposed reaction mechanism based on the experimental rate law. Consider the reaction where A plus 2B yields D. The experimentally determined rate law is rate equals K times the concentration of B squared. This tells us the reaction is 0 order with respect to A and 2nd order with respect to B. We are given a proposed 2-step mechanism. Step 1 is slow. B plus B yields C. Step 2 is fast. A plus C yields D. Our goal is to see if this mechanism is consistent with the experimental rate law. Here are the 2 rules for evaluating a mechanism. First, the elementary steps must add up to the overall balanced equation. Second, the rate law predicted by the slow step must match the experimentally determined rate law. Let's check the first rule. Adding the 2 steps, we get B plus A plus C yielding C plus D. Notice that C appears on both sides, so it cancels out. This leaves us with A plus 2B yields D, which matches the overall equation. So the first rule holds. Now for the second rule. The slow step is the rate-determining step. In this case, that is step 1. Remember, for an elementary step, its rate law is determined by its stoichiometry. So the rate law for the slow step is Rate equals K prime times the concentration of B squared. Now we compare this predicted rate law to the experimental rate law. The predicted rate law is rate equals K prime times B squared. The experimental rate law is rate equals K times B squared. They are identical. This means the proposed mechanism is consistent with the experimental data. C, which is produced in step 1 and consumed in step 2, is a reaction intermediate. We've seen that the rate constant K is temperature dependent. This relationship is precisely described by the Arrhenius equation. Our objective is to introduce the Arrhenius equation and explain its components. The Arrhenius equation is K equals A times E to the power of negative activation energy over R times T. It's a cornerstone of chemical kinetics. Let's break down the terms. We know K is the rate constant, T is the absolute temperature in Kelvin, E sub A is the activation energy, and R is the ideal gas constant, 8.3114 joules per Kelvin mole. The term E to the power of negative E sub A over RT represents the fraction of molecules that have kinetic energy equal to or greater than the activation energy. As we saw with Maxwell-Boltzmann curves, this fraction increases as temperature increases and decreases as activation energy increases. This term mathematically describes that relationship. The final term, A, is the Arrhenius factor, also called the pre-exponential factor or the frequency factor. It's a constant that accounts for two things: the frequency of collisions between reactant molecules and the probability that those collisions have the correct orientation for a reaction to occur. In essence, A captures the how often and how correctly collisions happen, while the exponential term captures the how energetically they happen. We can see the relationship between temperature and rate more clearly by looking at the equation. As T increases, the negative exponent becomes less negative, so e to the power of negative E sub A over RT becomes a larger number. This results in a larger K, and therefore a faster reaction rate. This equation provides a precise, quantitative description of how temperature accelerates reactions. Analyzing the Arrhenius equation directly can be challenging due to the exponential term. Fortunately, we can linearize it to make analysis much easier. Our objective is to convert the Arrhenius equation into its linear form and analyze it graphically. We start with the Arrhenius equation. K equals A times E to the negative E sub A over RT. To linearize it, we take the natural logarithm of both sides. The logarithm of a product is the sum of the logarithms, so ln K equals ln A plus ln of E to the negative E sub A over RT. The ln and E cancel out. This simplifies to ln K equals ln A minus E sub A over RT. It's often helpful to rearrange this slightly to match the standard equation of a straight line. We can write it as ln K equals negative E sub A over R times 1 over T plus ln A. Now compare this to the equation y equals mx plus c. We can see a direct correspondence. If we plot the natural logarithm of the rate constant, ln kk, on the y-axis against the inverse of the absolute temperature, 1 over T, on the x-axis, we should get a straight line. The slope, m, of this line will be equal to negative activation energy over r. So, we can determine the activation energy from the slope of the graph. The y-intercept c will be equal to the natural logarithm of the Arrhenius factor, ln A, from which we can find A. This linearization provides a powerful way to extract two key kinetic parameters from experimental data. Let's work through an example of using the Arrhenius equation to determine the activation energy. We will use the linearized Arrhenius equation to calculate E sub A from two data points. Suppose the rate constant K for a reaction was measured at two different temperatures. At a temperature of 25 degrees Celsius, the rate constant K is 0.033. At 75 degrees Celsius, K is 0.23. Our goal is to find the activation energy, E sub A. First, we must convert the temperatures to Kelvin. 25 plus 273.15 is 298.15 Kelvin. 75 plus 273.15 is 348.15 Kelvin. We can derive a useful two-point form of the Arrhenius equation by setting up the linear form at two different temperatures. After rearranging and combining, we get The natural log of K2 over K1 equals negative E sub A over R times the quantity 1 over T2 minus 1 over T1. Now we can substitute our values into this equation. The natural log of 0.23 over 0.033 equals negative E sub A over R times the quantity 1 over 348.15 minus 1 over 298 PE. Calculating the left and right sides, we get 1.93 equals negative E sub A over R times negative 4.83 times 10 to the negative 4. Rearranging to solve for E sub A, we get E sub A equals 1.93 times R divided by 4.83 times 10 to the negative 4. With R as 8.314 joules per Kelvin mole, this gives us an activation energy of approximately 30,200 joules per mole, or 33.2 kilojoules per mole. We have successfully calculated the activation energy from the rate constants at two different temperatures. We've covered a wide range of topics in kinetics. Let's recap the key concepts before we move on to practice questions. We started with the qualitative explanations of collision theory and its criteria for successful collisions. We then introduced activation energy, E sub A, as the energy barrier and visualized it on reaction energy profiles. We used the Maxwell-Boltzmann distribution to explain the effects of temperature and activation energy on the fraction of successful collisions. We then introduced catalysts as agents that lower E sub A and explained the difference between homogeneous and heterogeneous catalysis. We then shifted to a quantitative description. We defined the rate law and the orders of reaction, emphasizing that they are determined experimentally. We explained how to deduce a rate law from initial rates data and used it to calculate the rate constant K and its units. We discussed reaction mechanisms, molecularity, and the rate-determining step. Finally, we explored the precise temperature dependence of the rate constant using the Arrhenius equation. We saw how to linearize it to plot ln K versus 1 over T and determine the activation energy from the slope. These tools allow us to predict and control the speed of chemical reactions. Now it's time to test your understanding with some IB-style practice questions. Here is question 1. The diagram shows the Maxwell-Boltzmann distribution of energies for molecules at a constant temperature. E sub A represents the activation energy. Part A asks you to identify the significance of the area shaded in pink. Part B asks you to sketch a second curve to show how the distribution changes at a lower temperature, T prime, and to shade the new area corresponding to the fraction of molecules that can react. Take a moment to pause the video and work out your answer. Okay, let's go over the solution. For part A, the area shaded in pink represents the number of molecules with kinetic energy equal to or greater than the activation energy. These are the molecules that can lead to successful collisions and product formation. For part B, a lower temperature T prime will have a curve that is higher and shifted to the left, with a peak at a lower energy. The area to the right of E sub A will be smaller, correctly showing that fewer molecules have enough energy to react at a lower temperature. Let's try a question involving reaction order. Here is question 2. The data below were collected for the reaction A plus B yields C. Deduce the rate law for this reaction and calculate the value and units of the rate constant. The data table shows 3 experiments with different initial concentrations of A and B and the corresponding initial rates of reaction. The general rate law we're looking for is rate equals K times concentration of A to the X times concentration of B to the Y. Pause the video here and work through the problem. Let's review the solution. To find the order with respect to A, we compare experiments 1 and 2. Doubling the concentration of A from 0.10 to 0.20 causes the rate to increase fourfold, from 2.0 times 10 to the negative 3 to 8.0 times 10 to the negative 3. A fourfold increase from a doubling of concentration means the reaction is second order with respect to A. For the order with respect to B, we compare experiments 1 and 3. Doubling the concentration of B from 0.1 to 0.20 causes the rate to double, from 2.0 times 10 to the negative 3 to 4.0 times 10 to the negative 3. A doubling of rate from a doubling of concentration means the reaction is first order with respect to B. Therefore, the rate law is rate equals K times concentration of A squared times concentration of B. The overall order is 2 plus 1, which equals 3. Now let's find K using experiment 1. Rearranging the rate law, K equals rate divided by A squared times B. Plugging in the values, K equals 2.0 times 10 to the negative 3 divided by 0.1 squared times 0.1. This gives us a value of 2.0. Finally, for the units. The units are m per second divided by m cubed, which simplifies to m to the negative 2s to the negative 1. Here's a conceptual question about catalysts. Question 3. A reaction has a rate equation of rate equals K times concentration of A. An enzyme is added to the reaction. What effect will the enzyme have on the values of the activation energy E sub A and the rate constant K? Explain your reasoning. Think back to how catalysts work. You can pause the video to consider your answer. Let's look at the solution. An enzyme is a catalyst. Catalysts work by providing an alternative reaction pathway with a lower activation energy. So, the activation energy, E sub A, will decrease. A decrease in activation energy means that a larger proportion of molecules will have enough kinetic energy to react. Now let's think about the rate constant K. The Arrhenius equation shows the relationship between K, A, E sub A, and T. With a lower activation energy, the exponential term e to the negative E sub A over RT becomes larger. This results in a larger value for the rate constant, K. A larger rate constant means a faster rate of reaction. The enzyme does not change the Arrhenius factor A, as it doesn't change the collision frequency or orientation probability. It only changes the energy required for the collision. Here's a question on reaction mechanisms. Question 4. The reaction 2NO2 gas plus F2 gas yields 2NO2F gas. The proposed mechanism is shown. Part A asks you to identify the molecularity of each step. Part B asks you to write the overall chemical equation. Part C asks you to identify any intermediates and transition states. Part D asks you to deduce the rate equation consistent with this mechanism. And Part E asks you to explain why termolecular elementary steps are rare. Pause the video and try to answer these 5 parts. Let's review the solution. A. Molecularity is the number of reacting particles. Step 1 involves 2 molecules, so it's bimolecular. Step 2 also involves 2 molecules, so it's also bimolecular. B. To get the overall equation, we add the 2 steps. The fluorine atom F appears on both sides and cancels out, leaving us with 2NO2 plus F2 yields 2NO. Goof. C. An intermediate is formed in one step and consumed in a later step. Here, F is the intermediate. A transition state is the high-energy species at the peak of each step's energy profile. D. The rate equation is determined by the slow step. Step 1. Since it's an elementary step, its rate law is rate equals K times concentration of NO2 times concentration of F2. E. Termolecular steps are rare because they require 3 particles to collide simultaneously, which is statistically improbable. The chance of this happening effectively is very, very low. For our final question, let's bring back the Arrhenius plot. Question 5. The graph shows a linearized Arrhenius plot for a reaction. The y-axis is ENK, and the x-axis is 1 over T, in units of Kelvin to the negative 1. Part A asks how to calculate the activation energy, E sub A, from the graph. Part B asks for the value of the Arrhenius factor, A. And Part C asks how a change in temperature would be represented on this graph. Pause the video and apply what you've learned about the linear Arrhenius equation. Let's review the solution. A. The linearized Arrhenius equation is y equals mx plus c, where y is ln k and x is 1 over t. The slope, m, of the line is equal to negative E sub a over r. Therefore, the activation energy, E sub a, can be calculated as the negative of the slope multiplied by the ideal gas constant r. B. The y-intercept of the line is c. From the linear equation, we see that c is equal to the natural logarithm of the Arrhenius factor, ln a. To find A, we can calculate e to the power of c, also written as exp c. Temperature is inversely proportional to the x-axis, 1 over t. An increase in temperature means 1 over t decreases, which corresponds to moving left along the x-axis. A decrease in temperature means 1 over t increases, which corresponds to moving right along the x-axis. So, a change in temperature is represented by moving along the straight line. That brings us to the end of our in-depth look at the rate of chemical change for IB Chemistry HL. We've covered the fundamental theories, the factors that control rates, the mathematical tools to analyze them, and the role of catalysis in providing alternative reaction pathways. Mastering these concepts is essential for success in your IB examinations and for understanding the broader world of chemistry. Thank you for watching. If you need further assistance with this or any other topic, please remember that DAR Tutors offers expert, personalized tuition to help you excel. For expert tuition in IB A-Level and IGCSE curricula, please contact DAR Tutors.